Hello students, today we are going to see two steps for solving maximum and minimum problems. Step 1 is setting up the problem, and for step 1 you have four parts. In the first part we are said to read the problem very carefully, give names to unnamed or relevant variables, and note the main relations among the variables. And secondly, we can draw a figure if it helps us. Thirdly, we have to identify the quantity which should be maximized or minimized. And the fourth point is that we should make sure that the important and unimportant informations are clearly identified. Okay. So, in order to understand step 1 properly, let's see how we can solve for the four problems we are assigned and how we can apply the step 1 on these problems. Let's see the first problem. We can see the first problem is that a shepherd lives on a straight coastline and has 500 meters of fencing with which to enclose his sheep. Assuming that he uses the coastline as one side of a rectangular enclosure, what dimension should the rectangle have in other than the sheep, have the largest possible area in which to graze? So a shepherd has some sheep and he has a rectangular area enclosure. One side of the rectangular enclosure is the coastline, the sea, and obviously that side need not be fenced. Okay, so this is the sea, and the shepherd has a rectangular enclosure like this. So this is his uh, land where his sheep graze. See, the sheep are here. Okay, so they graze here, and the thing is, what we have to do is uh, we have to identify the largest possible area such that the sheep can graze the maximum. Okay, obviously we need to feed the sheep with maximum possible feed or food. So what is the maximum possible area such that this happens? So what all are given? We are given about uh, the coastline and coastline. Okay, so this side is coastline as we have said. So you have the sea here. Here you have the sea. So no fencing is required here. It is the coastline. So we have to do the fencing on this part 1, 2, and 3. And it is given that it has 500 meters of fencing. So suppose if this is length L and this is width W and this is width W, we are given that L plus W is equal to 500. That is 2W, L plus 2W is equal to 500. That is one among the observations you get from there. Okay, so let's see in detail how you can solve for it. So here you can see the same figure. Here you have the sea, the coastline, and the shepherd has the rectangular enclosure with three side of the rectangle having the fences. So if this is L, this is W. As we said, we have L plus 2W is equal to 500. Okay, and also we know that product of the length and width will be the area of the rectangular shape. So you have if suppose A is the area enclosed. A is the area enclosed. We can say that A is equal to L into W. Okay. So first what we did, we had understood the problem given to us, and then we draw a picture, and then we are assigning the variables. Here we have the variable L to be the length of the rectangular enclosure, W to be the width of the rectangular enclosure, and you have given capital A to be the area enclosed, and then you identified the equations. A is equal to LW and L plus 2W is equal to 500, as we said before. And what we have to do is we have to maximize this capital A. That is our problem. So that was problem 1. So let's see what is problem 2. Problem 2 is illumination from a point, light source. Okay, so you have an illumination. Okay, so you have a bulb here. So you have illumination here from a point. Point light source is proportional to the intensity of the source and inversely proportional to the square of the distance from the uh, point of observation. Okay. Given two point light sources 10 meters apart. So you have a light here and you have a light here. Okay. So we are given that they are 10 meters apart. Okay. And 10 meters apart with one source 4 times as intense as other. Find the darkest point on the line segment joining the sources. So this is a question. So you have the illumination from a point light source is proportional to the intensity of the source. So how will we understand and give various variables according to what we require? So here, as the same, this is the first bulb, this is the second bulb, and you can say that the first point is 0, and then after 10 meter, you have the second bulb, and call the intensity as I1 for the first bulb, and for the second one as I2. Okay. So as we said, we place the first source at x is equal to 0 and the second source at x is equal to 10 on the real line as in the figure. Now as we said, we denote I1 and I2 as the intensity of the two sources. Suppose L1 is the illumination. So you are taking a point x in between this two bulbs. So here you are given that uh, illumination from a point light source is proportional to the intensity of the source. So you have to have a point uh, from a point. So you have to have a point in between. So you gave the name x to that point, and the first one, you denote L1 to be the illumination at X from the bulb kept at 0. Okay. And L2 is the illumination from X at X from the second bulb kept 10 meters away from 0, right? So you have X here. The illumination coming from the first bulb from here and the illumination coming from the second bulb from here. Okay. And then we know that the total illumination will be the illumination of the first bulb plus the illumination of the second one. Okay. At that point x, right? So when we are standing at this point, light comes from here as well as light comes from here, so the total illumination will be adding up both the illuminations of the first bulb and the second bulb. Okay. Then you are given some conditions. Given 2 points, it said that with one source 4 times as intense as other. Okay. So that means suppose if we have I1 to be the intensity of the first bulb, the second bulb will have intensity 4 times that of the first bulb. So you call I2 is equal to 4I1. We are thinking I2 is having 4 times I1 as which is said in the word problem. Okay. And then it is said that The illumination from a point light source is proportional. Illumination, so you can say I1 is proportional to the the intensity of the source. So you have call it um, the illumination, right? So you have change there. See? The illumination. We know illumination is given L1, the denotation L1. L1 is proportional to I1. Okay. The illumination at the point light source is proportional to the intensity of the source. And also L1 is inversely proportional to the, it's given inversely proportional to the square of the distance from the source to the point of observation. So you have the distance will be x minus 0 the whole square. Okay. So you have L1 is proportional to 1 by, because it is inversely proportional, you have it is 1 by x minus 0 the whole square. Okay. 1 by x minus 0 the whole square. Okay, so that is equal to 1 by x square. So combining both, you have to give an equation. So you give a constant there. L1 is equal to k into I1 divided by x square. So that's what which is written here. Okay, so you have I2 is equal to 4I1 and L1 is equal to 4I1 divided by k square, where k is strictly greater than 0 is a constant we use to show the proportionality. So that is also called the proportionality constant. And L2 is similarly proportional to I2, and L2 is inversely proportional to the distance square. So you have distance square will be 10 minus x the whole square. That is, this is the distance in between the bulb and the point we have taken. So that will be L2 is proportional to I2 and L2 is proportional to 1 by 10 minus x the whole square. So combining both of them and making it an equation, you give the proportionality constant k. So L2 is equal to k into I2 divided by 10 minus x the whole square. And what we have to do is in the question we are asked to find the darkest point on the line segment joining the sources. That means the point where least light is there, right? So what we have to do is we have to minimize the total illumination. So we have to minimize L, which is equal to L1 plus L2. Okay. So these are the conditions which we obtained from the problem. Okay, that is the second problem. Now let's move on to the third problem. Third problem is given, we are given four numbers A, B, C, D. We have to find a number x which best approximates them in the sense that the sum of the squares of the differences between x and each of the four numbers is as small as possible. So we have to find a number x which best approximates them in the sense that the sum of the squares of the differences between x and each of the four numbers. So differences will be x minus a, then x minus b, then x minus c, and x minus d. And what you have to do is sum of the squares of the difference. So you have to take the squares of them, of each of them, of the differences, and then add them up. Okay, the sum of the squares, uh, sum of the squares of the differences between x and each of the four numbers is as small as possible. So what you have to do is, suppose if we give y is equal to x minus a the whole square plus x minus b the whole square plus x minus c the whole square plus x minus d the whole square, what we have to do is we have to minimize y. That is just our problem. So you can see the same given here. If we call the unknown number as x, we have to minimize y is equal to x minus a the whole square plus x minus b the whole square plus x minus a the whole square plus x minus d the whole square. So that was problem 3, how we make it into mathematical terms of minimization and maximization. Now the fourth problem is, suppose that it costs x square by 10 100 plus 10x cents to run your car for x days. Once you sell your car, it will cost you 50 cents a day to take the bus. How long should you keep the car? So you have day 1, day 2, and etc. And you have day X. Okay, okay, and so on. Okay, so you know that it costs uh, x square by 100 plus 10x cents units to run your car for this much number of days. Okay, if you are taking the car and using it for these much number of days, the total cost will be x square by 100 plus 10x. Okay, so we have to we are given that if we sell the car, suppose if you are selling the car at this day, so from that day you are taking the vehicle to be the bus. Okay, and you require 50 cents every day by bus. Okay, that means day x plus 1 you'll have 50 cents gone from your pockets. At day x plus 2 you again have 50 cents which goes from your pocket, and so on. Okay, so the question is, how long should you keep the car? That means here we are not given about any word about minimizing or maximizing or anything. So you have to infer from the question how to understand the concept. Okay. Here anyway, the matter which is important is that the cost of the journey or cost of the usage of vehicle. So anyway, whatever possible manner, always what we do is we have to reduce the cost. Okay, so you have to identify the day at which you have to sell your car, so that you have the least amount for the journey throughout. Okay, so we know that traveling by bus costs 50. Okay, so the day at which, okay, so you have a day at which uh, the per day cost of using the car is greater than or equal to 50. Okay, if you have a day at which a day a day at which the per day cost of using the car is greater than or equal to 50, then you stop the car then and there, and then you sell the car, because then from then on you understand that it will cost you more than 50, right? So then on you will start using the bus and you will sell the car. Okay, so you have to find that x, the day x at which the per day cost of using the car is becoming greater than or equal to 50. That is the idea. Okay, let's see the problem how it's said. So suppose if x is the number of days we run the car. Okay, and at this point in solving the problem, it is completely understandable that we don't understand what should be minimized, and it is not clearly stated in the problem as we said. So we have to understand and determine it ourselves. So generally, a reasonable objective is always to minimize the total cost, right? Or the total amount of money we have to pay. Okay, so how to do it? So you know that as we said, you know that the cost of running the car, the day at which the cost of running the car, the per day cost of running the car exceeds 50 cents per day, we should switch to bus, as we said. So suppose if y is equal to the cost per day running
per day of running the car at day X per day. So, as we said, this is actually the total cost of running the car till day X. So the per day can be calculated. It is the relative or the rate of change per day, right? So if Y is the cost per day of running the car at day X, we can understand that Y is equal to the rate of change per day. That is d by dx of what is given, the total, that is x square by 100 plus 10x. Okay, so you can calculate the d by dx. So you get 2x divided by 100 plus 10. So you have x by 50 plus 10. And also we know that y is greater than or equal to 50. Okay, that is what we identified from problem 4. So we applied the step 1 procedure of 4 points to the 4 problems which we were given. Now we will see what is step 2 and the corresponding points, and how we will apply the same to the problems which were given and discussed now. Okay. The step 2 of solving the problem: write the quantity to be maximized or minimized as a function of one of the other variables in the problem. This is usually done by expressing all other variables in terms of the one chosen. Okay. Not any restriction on the chosen variable. Whatever variable we have, think about what restrictions are given in the problem. Then find the maxima and minima by methods we discussed earlier in the chapter, and then state the answer in words. So that is step 2 of solving the problem. So let's see how we can solve the problem. So you know this first problem which we discussed is about the shepherd. Okay, and we mathematically formulated the shepherd problem like this. We have to maximize the area A, which is equal to LW, and we also know that L plus 2W is equal to 500, right? So we are going to use the same and solve the step 2 points for this problem 1. So here we have to maximize A. So we will write the uh, function A as L or W. Okay. Uh, we are choosing W. We have L plus 2W is equal to 500. So we can write L in terms of W. That is L is equal to 500 minus 2W. Also we know that A is equal to LW. So instead of L you can write 500 minus 2W into W. So when you multiply you get A is equal to 500W minus 2W square. And also you can understand, you have to understand the restriction of W. See here L is given as 500 minus 2W. So consider W to be 250. If you take W to be 250, because you know 2 into 250 is equal to 500, you get L is equal to 0. So if you have W to be greater than 250, what happens is 500 minus that value will become a negative value, but length cannot be a negative value. So the maximum possible value that W can take will be 250. So we can say that the variation of W will be definitely from 0 and 250. That is, the restriction on W is 0 less than or equal to W less than or equal to 250. Uh, Here, as we said, only a non-negative W can be meaningful, and W cannot exceed more than 200, because otherwise L would be becoming a negative number. Okay. So what you have to do is we have to maximize A, which is equal to, as we found out, it was LW. So it was converted in terms of W into terms of W. So you have maximize A is equal to 500W minus 2W square on the region 0 less than or equal to W less than or equal to 250. Then what you do is you find the derivative of A with respect to the variable W, that is dA divided by dW. That will be 500 minus 4W. Okay, and then you equate dA by dW. So presently what you have is
You have A is equal to 500 W minus 2W square, and we have to maximize it. That is our uh, problem. And you have the variation of W in between 0 and 250, right? So then the next step you have to do is you have to find the derivative of A with respect to the variable W. So you have that to be equal to 500 minus 4W. Then you have to equate dA by dW to 0. So that will imply 500 minus 4W is equal to 0, implies W is equal to 500 by 4, which is equal to 125. So you have W is equal to 125 now. Okay. Then what you have to do is you have to again use the second derivative test. So using the second derivative test, d square A by dW square will be equal to minus 4, which is strictly less than 0, and d square A by dW square at 125, at W is equal to 125. That is also equal to minus 4 because it is a constant that is strictly less than 0. That means by second derivative test you are getting that W is equal to 125 is a local maximum, and here we are saying that it is a maximum in the prescribed restriction from 0 to 250. You can understand that it is a maximum point. So the rectangle that is the maximum point 120 125. So when W is equal to 125, we know that L is equal to 500 minus 2 into 125, which is equal to 500 minus 250, which is equal to 250. So you have W is equal to 125 and L is equal to 250 to be the answer, and at those points you will have the maximum area of grazing land for the sheeps. Okay, for the sheep. So the rectangle should be 250 meters long in the direction parallel to the coastline and 125 meters in the direction perpendicular to the coastline in order to enclose the maximal area for the grazing land. Okay. The next problem was with respect to the lighting, the bulbs, illumination. So from the problem, we arrived at some mathematical terms here. We gave L1 to be the illumination. We first of all fixed a point X in between 0 and 10, that is between the two bulbs. And at X is equal to 0, you have the first bulb, and X is equal to 10, you have the second bulb. I1 and I2 are the intensities of the two sources, and we said that L1 and L2 are the illumination at X from the first source and at X from the second source, and we call total illumination as L, and we gave the three equations from the problem, right? So what you have to do is we have to find the darkest point, so you know that it is to minimize the illumination. So definitely you have minimize L. That is our main step. So let's see how you can do. So we have to minimize the value for L, which is equal to L1 plus L2, and you know that L1 is equal to KI1 divided by X square, and L2 is equal to L2 is equal to here you had L1 is equal to KI1 by X square, and L2 is equal to KI2 by 10 minus x the whole square, and earlier it was said that I2 is equal to 4I1. So that is an observation which can be put in here. So you have L2 is equal to 4k I1 divided by 10 minus x the whole square. So L1 plus L2 will be together. We can take k I1 out. So you have 1 by x square plus 4 by 10 minus x the whole square. Okay, so that is what which is written here. Okay, since the point is in between the sources, we definitely should have x to be in between 0 and 10.
So you have to minimize L in between 0 and 10. Okay. Then what you do is you have to, so you have L to be this value. Then you have to find the derivative of L with respect to x. So L you have to be equal to k I1 into 1 by x square plus 4 by 10 minus x the whole square. Then what you have to do, you have to take the derivative of L with respect to x. So you have that to be equal to k I1 into minus 2 by x cube plus 4 into 2 into 10 minus x divided by uh, 10 minus x, the whole raised to 4. 10 minus x the whole cube, right? So then you have uh, you can take 2 out, so you have 2ki1 into minus 1 by x cube. Yes, here you have 4 by plus 4 by 10 minus x the whole cube. Here you have 4, right? So when you solve for that, you get this, and then you have to equate dl by dx to be equal to 0. So you have this to be equated to 0, then 2k I1 is a constant, so you have minus 1 by x cube plus 4 by 10 minus x the whole cube to be equal to 0. So you have 4 by 10 minus x the whole cube is equal to 1 by x cube. Then you rearrange, you take the cubes first. You take the cube root. So you have and rearrange, cross multiply. So you have here 10 minus x divided by x is equal to cubic root of 4. So 10 minus x minus cubic root of 4 into x is equal to 0. Then you rearrange, take this minus x and minus a cubic root of 4x to the other side, and then take x out, and then in finally you get x is equal to 10 divided by 1 plus cube root of 4. So that is the critical point. We have to check whether it is uh, having a minimum or maximum point. For that, you take a point to the left of. We can either find the second derivative using the second derivative test. You can do it, but it is a little difficult. So what you do is you can take a point to the left of this point, and you can take a point to the right of this point. Okay, taking a point to the left of this point, the point we take is 0.0001. Note that we are taking points from 0 to 10. Okay, so the point will be this, and when you find the value for L dash, you get that to be equal to, that will be strictly less than 0. You find the values using a calculator, you get that to be strictly less than 0. And similarly, you take the value x to the right of that point. You can take x plus as 9.99999, which is very close to 10. The other was very close to 0. Okay, and then you find the L dash at that point, then you get that point to be strictly greater than 0. That means L dash changes from a negative value to a positive value. And from what we have earlier learned, that will mean the presence of a local minimum point, and here you are calling it a minimum point. So definitely that will be a darkest point, because it is having the minimum illumination. And using your calculator, you can get the value, the decimal value of the x, which is equal to 10 by 1 plus cubic root of 4, which is approximately equal to 3.86 meters. So that is how you find the second problem. And the third problem was to minimize y is equal to the difference, the sum of the squares of the differences of the point and A, B, C, D. Okay. So we said that y is equal to this, and we don't have any restrictions on x. Okay. Then what you do is dy by dx, find dy by dx. So you have 2 into x minus a plus 2 into x minus b plus 2 into x minus c plus 2 into x minus d. And when you simplify it, you get 2 into 4x minus a minus b minus c minus d, and equate it to 0. When you equate it to 0, you get equate dy by dx is equal to 0. That will imply 2 into 4x minus a minus b minus c minus d is equal to 0. So 4x is equal to a plus b plus c plus d. That means x is equal to 1 by 4 a plus b plus c plus d. So that's what which is written here. And then what you do is you try to find again, you can use a second derivative test. So d square y by dx square, that will be, this is dy by dx, that will be 8, 8. And you know that d square y by dx square at any point will be 8, because it is a constant number. It is strictly greater than 0. That means at this point, at the given point, the derivative, second derivative is strictly greater than 0. That means it is a local minimum point. So we had to minimize the value for y. So here you obtain that the x, which is equal to 1 by 4 into a plus b, b plus c plus d, is a minimum point at which y is having the minimum value. So the number required is thus the average. Average, that is a plus b plus c plus d divided by 4. That is the average value of the points. Now the problem 4, we know about the car, right? That was a problem. We understood that. How did we solve the problem here, right? Yes, we had the car, and we said that we have to minimize the amount we have to pay. So the end of the problem, at the end of the problem, we said that y is, whenever y is greater than or equal to 50 and y is equal to the uh, derivative of x square by 100 plus 10x, which is equal to x by 50 plus 10, the corresponding value will be the minimum, the number of days at which we have to sell the car, so that we have the minimum amount to be paid. So it cannot be called a maximum minimum problem, standard maximum minimum problem. We have to minimize the expenses by selling the car at the time when the cost per day, which is we found it to be dy by dx per day, right? Per day was dy by dx, which we found at x by 100, x by 50 plus 10, and that reaches the value 50. When it reaches the per day value, uh, per day expenses of the car is reaching the value 50, we will sell the car. So we will solve x by 50 plus 10 is equal to 50. That will mean x is equal to 2000. So we will keep the car till 2000 days, and then after these after or on the day 2001, we will sell the car and move on to using the bus. So that cannot be called as a standard maximum minimum problem, but a workout in the similar area. So we just took 4 problems, and we applied the step 1 procedure and step 2 procedure on the 4 problems. And uh, that is the end of this session. And next you will have similarly how to solve maximum minimum problems from example 8 to example 12 in the next session. Thank you.